Hello, and welcome to Team 19's High Altitude Aircraft Analysis.
For this design analysis, the goal was to model an aircraft capable of supersonic high-altitude cruise. Many of the design parameters would be modeled from the U-2 spy plane as this aircraft fit the desired mission profile. One of the major questions covered in the analysis is the merits of using an afterburning engine in the design. The assumptions and requirements section covers many of the performance specifications for the aircraft being modeled, such as lift-to-drag ratio and desired cruise Mach. The approach taken for the analysis as a whole consisted of creating a MATLAB model that was capable of simulating the conditions in each stage of a turbojet engine. This analysis was then applied over a wide range of altitudes to observe the changes in performance, both with and without an afterburner. Overall, our design was modeled to operate at a specific set of high-altitude conditions, and the performance at other altitudes deviated from our performance specifications.
U-2 was designed back in 1955 with the help of the CIA, Air Force, and Lockheed Aircraft Company. The United States government wanted a plane that would be able to spy on the Soviets and remain undetected. This required the aircraft to fly over 70,000 feet and carry a camera with a high enough resolution to spot ground targets from elevation. The team designated for the U-2 project spent 12 months modifying the engine to get 11,500 pounds of force from the Pratt & Whitney J57P37 engine. The redesigned engine had a fuel consumption of 9,000 pounds per hour at sea level and 7,000 pounds per hour at the 70,000 foot cruising altitude. Similar to the objective of the U-2, NASA's Helios prototype was tasked with flying nearly 10,000 feet for 24 consecutive hours. They reached the first goal by reaching a height of 96,893 feet and maintaining a height of over 96,000 feet for 40 minutes. The Helios prototype has a wingspan of 247 feet. This aircraft is powered by 14 electric motors, which are spread across the entire length of the wings, and each motor is rated at 1.5 kilowatts and drives two blade propellers with a diameter of 79 inches. A high-altitude aircraft analysis would be incomplete without exploring the aircraft holding the title for the highest altitude achieved. In 1977, Alexander Fedotov took his MiG E-266M, an experimental aircraft of the MiG-25 program, to a height of 123,523 feet. The MiG E-266M featured two turbojet R-15BF2 300 engines. These engines produced 16,523 pounds of force on their own and 22,503 pounds of force with an afterburner. This resulted in thrust-specific fuel consumptions of 1.25 and 2.7 with an afterburner. It had an overall pressure ratio of 4.75 to 1 and a maximum turbine inlet temperature of 1,215 Kelvin.
On May 1st, 1960, a U-2 spy plane flying in Soviet airspace was shot down and pilot Francis Powers was captured. The plane that was shot down was part of a larger plan to gather information about the Soviet Union military technological advancements. This plan was approved by Dwight Eisenhower, the president at the time, who was fearful of the Soviet Union's claims about the strengths of their nuclear powers. The Soviets were aware of the U-2 spy planes for years, but could not reach them until they developed the missile that shot down this plane. Francis Powers was captured and had no choice but to reveal his mission. He was later convicted on espionage charges and sentenced to 10 years in prison. The U-2 incident occurred only days before the Paris summit, where Eisenhower hoped to come to new agreements with the Soviet Union on nuclear policies. This hope did not come to fruition as the Soviet Union leader Khrushchev no longer wanted to cooperate with Eisenhower. The relationships between the US and the USSR were hindered even further for future presidents due to this event.
Our design requirements were determined by looking at existing vehicles and taking averages of certain characteristics like wing geometry, cruising altitude, max takeoff, and empty weights. Using a little lifting line theory and the basic lift equation, the following input characteristics are given as the benchmarks for our system. Also assumed were component efficiencies given in Hill and Peterson textbook, and that the diffuser had one inlet normal shock. The last assumption caused some major limitations in the ceiling of our design and reinforced the importance of reducing the impact of inlet shocks for supersonic diffusers. The analysis that follows includes not only these design parameters, but applies the optimum at our desired cruise across all altitudes to determine not just cruise, but also climb and takeoff performance. The two major performance graphs from our analysis are given here. The left graph gives the two major performance metrics of specific thrust and thrust-specific fuel consumption, as well as total fuel consumption rate. The right gives graphs of the estimated range and endurance of the aircraft. The most obvious characteristic of all the graphs is a sharp asymptotic change of TSFC, range, and endurance as we approach a ceiling of 70,000 feet, while specific thrust gradually declines. This is primarily due to the large normal shock assumed at the diffuser entrance. A good guess as to why is that at this flight speed, around Mach 3, the shock starts to detach from the diffuser inlet and is even less efficient than if attached. Additionally, this is the point when the stagnation temperature of the flow reaches the max turbine inlet temperature, meaning that the fuel consumption rate approaches zero. This is the cause of the asymptotic jumps. Eventually, the fuel rate becomes negative, as the only way to produce a sensible thrust value is to decrease the energy of the flow in the engine, which violates the second law of thermodynamics and leads to the service ceiling we see in the graphs. The second and more important observation is that for the majority of altitudes, our performance metrics remain constant. This is due to the happy accident that in order to maintain lift, the momentum of air flowing over the wings and entering our engine remains constant. As the density increases, the airspeed has to increase similar to a square root curve. This means the engine is able to output a consistent amount of thrust regardless of flight condition, so as long as shocks are not dominant in the flow. Last and most interestingly, despite the low endurance, the range is on the order of 12,000 miles. This means that the hypothetical aircraft could go halfway around the Earth, take surveillance pictures, and return all in around 90 minutes or around an hour with the afterburner engaged. Presented here is the takeoff analysis. These values were determined by setting the initial speed entering the diffuser to be 0 and evaluating the thrust and fuel consumption with and without the afterburner. In order to determine takeoff distance, a differential equation assuming a linear dependence of thrust on velocity was used to yield a minimum takeoff runway length just shy of 5,000 feet. The typical runway at a major U.S. and military airports is between 8 and 12,000, so an aircraft equipped with our propulsion system is more than capable of takeoff at pretty much any large airport in the country.
In conclusion, our analysis succeeded at modeling the basic performance parameters of high-altitude turbojet propulsion. To make a future analysis more accurate and complex, a few steps could be taken. Firstly, we could better model the effects of oblique shocks at the engine inlet. Currently, the shocks are modeled as a single normal shock to make the MATLAB analysis simpler. The inclusion of oblique shocks would decrease stagnation pressure losses at the inlet and thus increase our maximum flight altitude. A variable nozzle could also be included to account for the wide range of ambient pressures encountered at different altitudes. This concludes our presentation. Thank you for your time.